Good morning, everyone. Thank you for being here. I'm Aggelos Biboudis, and I'm going to talk about today streams a la carte and how we introduce extensible pipelines by employing the design pattern of object algebras. This is a joint work with Nick Palatinos, who works for Nessus Information Technologies, George Fortounis, who is a postdoc in our lab, and Yannis Maragdakis, who is our advisor from the University of Athens. Today I'm going to talk about streams, but streams is a pretty overloaded term these days. It can mean anything about reactive programming, lazy list, streams for big data scenarios, and stuff like that. But our main focus is about functional-inspired pipelines that we have borrowed from the functional world and imported to the object-oriented one, and has all this set of very beautiful combinators to operate on streams and on collections, for example, filter, map, etc. And our focus is that these libraries are lazy. We get back transformed elements from some source only when they are needed. This snippet over here is an actual Java 8 snippet from the newly introduced Streams API in Java 8. And it's a stream of integers that is backed by an array named V. We use filter to filter elements, map to map them, and sum just to reduce the collection to a single number. And stream libraries are everywhere. There is a great implementation variety. For example, in C# we have link, in F# we have sequences, in Scala we have views, and they all implement pull streams. While Java 8 uses another directions, has employed another direction and implements push-based streams. So what's missing from current libs? All these libraries, they have either a fixed behavior in their semantics of how they construct pipelines, or a fixed set of operators of both, or both. And we really want to be able to abstract the logic that our pipelines are constructed, and we want to use pluggable semantics. For example, to have a really nice pipeline with filter, map, and sum, but we want to be able to set the semantics of this pipeline. And we also want to retain the ability to retrofit new operators in the library. So, why we really need pluggable semantics? Because some operators are fundamentally push or pull, and this has implications in performance. For example, the zip operator, where you take an element by element sequence of various streams from 2 streams or more, and you zip together, this is in nature a pull operator, fundamentally pull. And we also want to support mixed-in functionality. So, for example, we have a bare query that is executed in push style, and we also want to log. So we can have 2 kinds of interpretation and mix them together, or fuse a pull kind of interpretation, or to have blocking or not pipelines with either push or pull. But let's go through some basic background first for 2 slides. What is a push-based stream and what is a pull-based stream? First of all, they both are lazy. And let's see a little bit the consumer side of both streams. Let's go to the more intuitive one, which is the pull stream. We create a pipeline, source v, .map, where we increment each element, and we get back a pool of integer stream. What essentially is this is an iterator. And we can drive this iterator by invoking hasNext and next, get back the transformed element, and use this element in whatever way we want. So we say that because we control the stack on the consumer side, this kind of laziness is lazy in the consumer side. On the other hand, a push-based stream does not have an explicit loop. A push-based stream is essentially a function, a composed function, that somewhere in there is a loop that is going to be triggered by evaluating this function. And we should pass to this function a function as an argument that knows what to do with the values. So because the loop code is somewhere hidden in there, we say that laziness, this kind of laziness, is in the producer side. So this is our distinction. And let's go at the producer side for a bit. As we have said, pool-based streams are basically an iterator. So when we create a pool-based stream with a source combinator, we just use an instance of an anonymous class that creates an iterator that knows how to traverse elements in the backing array. But on the other side, what we essentially create is a closure that has the loop code, the loop logic inside it, and we invoke the past method for each element. So you can see that the loop is on the producer side for push-based streams. And the difference in semantics is not just encyclopedic, not just academic. This is an actual Java 8 snippet that fails with an out-of-memory exception. And this is because in Java 8, we can go from the push world to pull by invoking the .iterator combinator. But we lose a little bit of laziness. So if we use inside the flat map operation as a mapping function an infinite stream, and we just enforce the side effects once, we can get an out-of-memory exception, because there is a buffer somewhere in there that tries to save all these intermediate results of just one evaluation of the infinite stream. So you heard me saying that we want to create a library that is extensible in two things. And at this point, I may add that we want to retain static type safety, and we want to do that without recompiling the code. So what we really seek is a solution to the expression problem, as was introduced in 1998 with Phil Wadler's mail. And we seek a solution to that problem in order to use that as the basis of our library. So 3 years ago, here at ECOOP, Bruno Oliveira and William Cook introduced Object Algebras as a design pattern of extensibility, as a solution to the expression problem, with a paper extensibility for the masses. And we use exactly that. Just a very brief look about what are object algebras. Let's say that we have a very small DSL, and we want to be able to create nodes of our programs with two factory methods. So we have an interface of an expression factory, and we want to create literals and add nodes. But in this example, exp is not abstract. Let's make that abstract. So in terms of object-oriented programming, this is a generic factory. So we have abstracted away the actual kind of nodes, right? And this is an example of the creation of this kind of expression, 1 + 2 + 3. And it's pretty straightforward. We have the expression factory parameterized by exp. I have named it f, and we invoke the factory methods on this object. And this query can be the body of a method that propagates correspondingly the type parameters. In the object algebras realm, I wanted to introduce this concept via factories. But in the object algebras realm, interfaces are called algebras, very simply. Implementations are called factories. And we can add new cases by extending the algebra. So if we have interface, we extend other interfaces, as we know, and to add new functions or new behaviors to our pipelines by implementing the algebra. So what we propose is a library design inspired by algebras. We provide extensible streams with pluggable operators, pluggable behaviors, and what we get for free is yet another way to pass mixed-in behaviors to our pipelines, so enhance them in some way. And of course, we want to, because we are talking about streams, we want to affect performance in a good way only, and not in anything, do anything bad. So we have two categories of combinators. One for intermediate operators, and the second for terminal. What is the object algebra of streams? As we have said, it's an interface that follows the object algebras pattern. And here are three combinators, source, map, filter, that creates something of an element that return the type of a stream of the type of the element. However, this, as you may notice, is not valid Java 8 code. We do not have support for higher kind types. So this C of underscore that I pass to stream algebra, to the stream algebra interface, is a unary type constructor that I have created in my mind just for exposition. And I'm going to use that through the slides, but at the very end, I'm going to tell you how we encoded higher kind types in a lightweight manner. And this is a very clever technique that we didn't introduce, but we find it elegant. We found it elegant, and we employed it. Again, what is the object algebra of streams for terminal operators? It is a new interface that extends what we have seen before, enhanced with another type. Not the type of the stream, C, but of the type of a container that contains a value. Because here we have terminal operators, count, that is going to produce a long, reduce, that is going to produce an integer. But we would like to abstract of what terminals do by introducing, by abstracting the container of some value. We will see later an example. So a recap, how do we extend streams? We add new operators by extending the algebra as we already did for the terminal operators that extended the algebra for the intermediate ones. And in this example, I introduced a new combinator that takes one parameter and the previous stream. We follow the pattern of all the other intermediate operators and returns the type of the stream. And we also want to add new behaviors by implementing the algebra, as I have said, and we do that by implementing the corresponding algebra. So if we want to create an object that holds all the logic for push-based interpretation of a stream pipeline, we create a push factory that implements the stream algebra of the type that I want to support, which is push. And what did we say earlier about push? That push is just a function type. So let's use a stream. It's a concrete stream in this slide. We create an algebra. We instantiate it. This algebra object, this alg project object, has all the logic that is needed to interpret the stream. And we can see the previous example that we saw before in the Java 8 snippet, but in a nested form. And we create our pipeline using the corresponding methods. So we want a sum of a mapped, of a filtered source. And this is in reverse order. Because I wanted to follow, to present snippets in Java. However, we have a way to restore fluency. For example, stream.source.filter.map.sum, but for Scala and C#, because there we have methods like extension methods and the cake pattern and stuff like that. But I'm going to stick to the plan here with Java 8. And semantics are a runtime parameter, so we can abstract away the algebra object as we did for our little DSL earlier, and we can parameterize a carte method by an algebra interface, and we can return the constructed object through the body of that method. And in that case, because I'm going to reduce to a long integer, we create, I return a container of long, sorry. And these are some use cases of the Cartesian product method that I created before. So for example, throughout our paper, we had created some various factories that I present here. For example, exec push factory that has all the logic for terminal intermediate operators for push-based semantics. The same for pool. We have created a fused pool one where it fuses all filters together and all maps together. We enhanced a push factory, an exec push factory with log factory. So upon evaluation, we also get some printing activity. We did the same with pool, and also we can get, instead of getting a simple long out of a pipeline, we can get a future of long. So this is why we abstracted terminal operators as well, because we can have blocking semantics to get the long right away, or to get back a future of long, and afterwards call the .get method in order to wait for the final value. And in the following, I'm going to present 4 benchmarks just to examine what happened with this new interpretation of pipelines. In the first benchmark, in all benchmarks, we have 2 axes. And on the vertical axis, we have average milliseconds per operation, and on the horizontal, we have the benchmark names. And in this benchmark, we can see that we measure Java 8 performance for 4 micro benchmarks, our pool algebra, and our push algebra. And at this point, we don't care about the differences that there are in this slide, but they all are on the same level. So we didn't lose anything in terms of performance by introducing object algebras, this design pattern. Object algebras are for construction only. So they didn't affect the performance of our pipelines. Let's have a look at what happened with the algebra that fused maps and filters together. Again, we have some columns that indicate Java 8 performance, a pool algebra, a push one, and a fused pool. The pool algebra that we have fused is with green, and the simple pool algebra is indicated with orange. So we can see that we have got a pretty good performance out of it. And as I have said before, in Java 8, we have a way to go from push-based streams to pool by invoking the .iterator method, but we lose a little bit of laziness. So in some cases, we really need a pure pool implementation. So we have created 3 benchmarks, count, and filter map count, where we have used the .iterator combinator, and then we got out of the iterator transformed values one by one on our own loop. So we can see that with a pure pool-based implementation, instead of going from push to pull in Java 8, we get very good performance. And let's see our pathogenic case from earlier. Earlier, I showed you an actual Java 8 snippet that emitted an out-of-memory exception because I created an infinite stream, and all these values had to go somewhere, and Java 8 didn't deal well with very large, with an infinite stream. Of course, we cheat here a little bit because it is a pathogenic case of Java 8 streams, which is by design. This isn't a bug that the Java 8 developers, who are very smart, have introduced. This reveals the deep nature of the push style of composition there. And we have this short-circuited Cartesian product, short-circuited because we use take. We use take to just take some elements. And Java 8 did pretty well at 40 or 50 milliseconds. Java 8 with an iterator, because we have lost a little bit of laziness, nearly doubled. But with a pool algebra, with very fine-grained laziness, because a pool algebra uses composed iterators, we could go element by element in the mapped stream in flat map that produces an infinite stream, and we were able to short-circuit on the take combinator very, very easily through that. And as a final remark, how did we encode higher kind types? We used a very clever technique already used in Java and C# libraries, like in the HiJ library, or in Maggie's answer, who is a user of Stack Overflow that analyzed his idea there. But it's also a recently presented technique in an OCaml publication named lightweight higher kinded polymorphism. So we employ the same encoding to provide lightweight higher kinded polymorphism in Java. It's a little more verbose, but it makes our pipelines work. And what we actually did, remember the stream algebra from before, that I have created in my mind a new unary type constructor there, C. What we actually do, what is the core idea, is that the type application is defunctionalized. And we return an application of C to T. And somewhere in there, there is a semi-type safe cast in a very centralized place that does the trick. That does the trick. There are more information in the paper. We use a static class, an inner static class that represents branding, which helps us through the type system, and every information is there. So, to sum up, we have a library implementation inspired by the design pattern of object algebras. We have used this pattern as the basis of our small DSL, because we regarded pipelines as a small DSL. We have extensible operators. We got pluggable behaviors. We have got a mixed in behaviors, log with something else, etc. And performance is still there. We didn't lose anything. We have an artifact. We can browse through the code, and all cases that were verbally presented in the paper have the corresponding test on this artifact. And I may take questions now. Thank you very much.
Question?
Thank you. Very nice talk. I find it very interesting. How can you interoperate with Java 8 streams? Can you take an Java 8 stream and pull it into your system, and vice versa? Can you take one of your streams and put it into Java 8?
Yes. Actually, so what I presented today and we present in the paper are sequential streams that we created the code. Java 8 streams has its own push-based implementation. Actually, what we have used is a reverse-engineered push-based implementation just for this part. And Java 8 streams are not extendable. They are in. You can implement the corresponding interface, but you cannot subclass the corresponding method because, as far as I remember, it's final. but we can delegate through the calls there to every corresponding method. So we can do that, and on top of that, we can act as a provider for other stream libraries as well, for example, that support this set of operators. But of course, it is a lot of engineering effort because you want to retrofit other implementations to this one. So as we had push factory, pull factory, maybe we could have a Java 8 factory or yeah, that's it.
Other questions?
So I really enjoyed that you could take very general techniques and then apply them to your specific problem. It was also nice to see you applying Jeremy's work. He's my student. Have you told him about this?
Jeremy? No.
Jeremy Yellop used to be my student.
No, I haven't. I haven't told him.
It's great.
I haven't told him. I will. It was a very good paper.
I should ask a question. So your benchmarks all look like micro benchmarks. They were just for tiny programs. Is that right?
Yes.
Have you tried it with macro benchmarks?
Not yet. Not yet, because we wanted to take a really small step and examine what happens with algebras, which are essentially tagless interpreters. And we wanted to see how this interacts at the stream domain. Because if you are going to speak about streams, you really want to see step by step what happens.
Sure, but now that you've got your stream library, it'd be interesting to apply to some big stream processing code and see what happens and see if by choosing your representation carefully you could get big improvements.
Yes, yes. Thank you very much.
Your design reminds me a bit of Clojure's transducers. So can you say a few words about how they compare?
Yes. Transducers, I'm not very experienced with Clojure and transducers, but transducers have a little bit of different type signature than our push-based streams. But I don't know the details. However, I have seen Rich Hickey's talk recently, and he also talked about push-based streams, that when you map an infinite stream inside flat map, you can get out 0, 1, or many more elements. And this incredible decrease in performance and increase in footprint also appears there as well. We don't provide the solution for that, even though we have come up with a solution to support that to base streams, to push streams. But if you use pull-based streams and go perfectly pure from the beginning, in a pull kind of way, then you solve the problem. So this pluggability gives us the opportunity to say, okay, let's go with pull on that.
Andrew? So I'm still trying to figure out exactly what a push-based stream is in Java. A pull-based stream is I understand the difference conceptually, but the pull-based stream is represented as an iterator, i.e. an object I can say next and has next. A push-based stream is represented as a function which, when I apply it, will apply the argument of that function to every element of the stream before giving me back control.
Yes.
And that's why, of course, it fails horribly
Yes.
on infinite streams.
Yes, it actually has the type signature of T to unit. This is a lambda to unit. So you return back a function, a closure, that has all the appropriate logic to traverse the array,
Right.
and applies to each element of the array a function that takes as an argument. Right. That lambda that knows how to handle transformed values.
And then throws away any result of that function. So it's like a do over the whole stream.
Yes, in these examples, yeah. But you can do a lot of clever tricks there to return booleans or to return some other structure in order to pass around information from step to step. And this type signature that I've told you right now is a reverse engineered signature that resides somewhere in Java 8 streams called try advance. I think try advance. So tries to advance, like in Java 8 streams
Right.
internals.
Isn't this exactly a Smalltalk do?
Perhaps, yeah.
I mean, an internal,
I have-
an internal iterator as opposed to an external iterator.
Yes. Yes, it is internal iteration. Not in the kind of way that, okay, you have a loop and the for each, the commercialized difference of external internal, but this is exactly what you told. Push-based is internal, pull is external.
Thank you. Let's do the rest over lunch. Thank you very much.
Okay.
Okay, let's thank Aggelos.